All right, so how you guys doing today? You okay. All right. So it's Friday, right? All right. So we're gonna continue on the chapter 19. So there are some other reactions I want to go over today. So this is the um, something we can do. And then we're gonna treat it with some. This is the something what we did before. So we're gonna use this one. And this is lithium dimethyl copper. Okay. Then what happens to this one here is you're gonna have this one lithium here, copper. Methyl groups are here, and then this goes to there, okay, and then this goes to on the top, so it will become negative charge once, and then this lone pair goes down again, so it's gone, and making this one carbonyl group again, and that makes this one the hydrogen group leave. Okay. So what happens to this one is you're actually going to have this one. So you have a third group R added to here. So you have this group to leave, and you have added on the one of the methyl groups on your copper, and just right there. So you have a ketone. Okay. So this is only part. This is a Gilman reaction we did on level 1. This is possible when you have really good leaving groups, which is this one. So this is a pretty good one. So you can have easily for this reaction. Okay. So if that is the case, maybe you can try this one. Okay, about 1 minute. Okay, so yeah, try to do this one, right? So trick is make this one leave. It's pretty good leaving groups, and switch this one to this one. So this is also the one way we can make a ketone. So I'll move on. Can I move on, right? I can move. All right. So the next one you can do is you can treat some aldehyde with some. You can treat it with the chromium trioxide with some acidic conditions in acetone, probably quite low temperature, and it should be in the aqueous solvent like water. Okay? So if you do this one, what happens to this one? This aldehyde become carboxylic acid compound. Okay. So this is what happened to this one over here. So what happens to this one here is first of all, they actually interact with water first. Okay. And so water goes there, okay. And then this will make push to this one, to this one. Okay. So if that happens, this is now a single bond. And then you have water. And and this will be grabbed by another water. So this will be gone, plus charge, and hydrogen will be gone, okay, over there. And then this, the negative charge oxygen will grab one of the proton over here. So they become hydrox group as well. So the negative plus will be gone like this. Okay, so in this case, do you guys remember this one? This will make, this is what we did on Wednesday. This will make this one alcohol what? To carbonic group again. So if this one comes in, and this is acidic condition, right? So this one will actually grab one of the hydrogen, because it's actually proton, sorry. And this will be gone, and this will be positive charge, and they're coming into this position. And then this will actually also gonna grab this one over here. Okay? And so this will goes to there, so this will be neutral. Okay. And then what happens to the here is the water comes in and try to grab one of the hydrogen here and goes to there. And then this bond will be broken and taking the hydrogen. So when it's plus charge, this is gone there. So the leave, and then this hydrogen taken by water goes to there, and then this bond between these two also leave to there. And this goes to, when it picked up the positive one, goes to there, and leaving as this one. And this will be carbonic groups. Okay. So yeah, this is what we did, but technically what you need to do is when boro first came in, there will be two hydrox group, but one of them will become the carbonic groups because of the chromium trioxide. So we'll have the carboxylic group over here. Okay. Carbonic group there. Okay. So what might be the trick here? So if you see this one with the chromium trioxide with acidic condition with water, you just need to switch this one to OH. That's the trick. Okay. You guys try this one. Very good. I think it's quite simple, so you can try 1 minute. Okay, so just gonna switch this one to hydrox group. Okay, it's pretty simple trick you can do, right? This one. So you don't have to do the mechanism, but with this simple trick, you can get this product compound. All right, so let's move on. So the next one I want to talk about is a bit weird. It's very strong oxidation that you're gonna see. So there'll be potassium permanganate with some strong base, okay, and some solvent there. And later we'll be treated with the hydrogen cation over here. So what happens to this one is they will become sort of this one over here. Okay. So you see what happens to here is they break this one and they put another carboxyl group with the hydrox group. So you have a two carboxylic group on these two sides. Okay. So this is very strongly oxidized, very strongly oxidized. So this is a hexane dioic acid. Okay. So this is kind of a really strong oxidation. So what happens to this one is simply this one. So you have a hydrogen implied here, right? And then this will be treated by base. We have a base over here. So technically, hydroxide anion comes in and try to grab the hydrogen over here. So it only takes the hydrogen cation. So this actually go to there. So then this will be gone. Okay. And there will be a double bond. So this will be pushed to there. So this will be gone. This will be negatively charged. Okay. So in this case, you have a permanganate over here. It looks like this. Looks like this. And then, as we know, the pair of electron, especially in the p orbital, can easily attack one of this one, okay, like this. Okay. So if that happens, what happens is, obviously this double bond will be gone, right? And then this will be this one like this, okay? So then what happens, this one is in a row, this goes to there, this will break, and this will goes to there, so it will be break too. And then, so this now bond is going to the oxygen here, so this will be broken, okay? And these two bonds will be broken too, okay? But there were 1, 2, so it'll be 2, so it'll be carbonic group right there. This will be, okay. So now you have this one, and then what happens to here is there's another, the permanganate is coming in, and they use the 1 oxygen, 1 out of 4 bound to here, okay, and then it goes down to the negative charge. This will be gone over here. Okay. So what happens here? The actually pair with the other cation, which is a potassium cation, right? And then if you treat with the strong acidic conditions, they can be replaced by what? Hydrogen cation. So they just what? Attack those two. So then what? Negative charge plus charge will be gone, right? And they just make two. So you have 2 carbonyl group with the what? Also the hydroxy group that makes what? 2 carbonyl groups over there. So it's very not carbon, sorry, carboxylic groups there. So this is the okay. So does it make sense? Yeah. So this is kind of something you can try. So yeah. Okay. So this one over here, just you have to break it. This one. Yeah, this is stuff you need to do. Okay. Does it kind of make sense? I know this is a kind of extreme case because it's really indeed very strong oxidation. But this is one thing we could also do, making ketone to carboxylic compound. Okay. All right, I'll just move on. I don't think I'll put this to the exam. Maybe not, maybe. But yeah, this is one thing we need to talk still about the ketone and aldehyde compound. So we good, right? Can I move on? Okay, so I'll move on to the next one is what we call the nucleophilic addition of maybe on aldehyde and ketone. So the basic rule is here. So the either aldehyde or ketone has what? The carbonic groups over here. And then they're going to have either 2 R's on the side, which will be ketone, and the other one will be just the one will be actually hydrogen just, so become aldehyde. And nucleophilic, literally, we're gonna add the nucleophile into it because if you look at the carbonyl group in your ketone or aldehyde, obviously your oxygen is relatively speaking more negative, and this is the positive. So this is the where that you're gonna see very electron poor carbon. So if it's really electron poor carbon, that means that makes this carbon to be quite strong electrophile, because the electrophile means they're lacking the electron density, so they're looking for something that is highly electron dense, which is our nucleophile. So our nucleophile, either negative charge or neutral, they should have a lone pair to donate the electrons. So that's why they can come into this position here. So if you look at this one over here, one carbonyl group had a double bond between carbon and oxygen here. They're either 2R or 1R and 1H. They should be on the plane because it's a trigonal planar. There's only 3 bonding. You guys remember this, right? The trigonal plane. So when they're all on the same plane right now, as in this chalkboard is. But this one has to come onto the either side, right? Either front or the back, right? So the angle is only because of this carbonyl group. When they're coming into this plane, either front or the back, it's about like a 75 degree. So it's not so enough space to going into that place, because eventually when they do this, they need to form what? They need to form a tetrahedral structure. When they remove it, so when they're coming in, this will be going to the oxygen. Okay. So will become. So if that happens, it has to be tetrahedral structure. This will go into that. Okay. So anyway, so this is happening here. So this is kind of the reason why you see the aldehyde will become more reactive with this type of nucleophilic addition. There's 2 main reasons here. So as you know, if you think of the steric hinderness, this ketone is actually linked to the, so these 2 R groups here, which is what? Much bigger than hydrogen and also a bit bulkier than hydrogen. So they're only coming into the 75 degree on the same, either front and the back. If they're bulkier, it's harder for the nucleophile to approach to the carbon in the carbonyl groups. So that is why statistically, aldehyde is more reactive than ketone. We'll show you one example soon today. It's hydration, but this is in. And also, if you think about the electronically, meaning think about the electron density on the compounds. This carbon here in this carbonyl group actually covered by these 2 R groups, which is what? There's some carbon there for sure, with other R type of groups, alkyl groups over here. So this is somewhat stabilized by those 2 neighboring carbon, okay? And when this carbon will be like withdrawing, the electrons around this carbon withdrawn to the oxygen because it's electron negative, but this can be somewhat stabilized by this carbon by what? Induction and hyperconjugation. So then, but this one is not. So this makes, there's only 1 carbon here. This is a primary, secondary here, this carbon. That makes this carbon more unstable, less stable. So that will be also more reactive. So if you have a compound that's becoming more stable, meaning they're a bit more inert to the reactions because they're already stable. But if it's not stable, they want to do the reactions to be more stabilized. So in that way, statically, electronically, aldehyde will become more reactive than ketone. Okay? Does it make sense? Okay. So 2 reasons here: static, electronic. So this will be on the example sure. So please remember this one. Okay. Because you have to know that why aldehyde is more reactive than ketone. Okay. Makes sense, right? Makes sense. Okay. All right, let's move on. So I'll give you one example here, which is hydration. Oh, so I'll give you the potential nucleophile first. Okay? So you can try to do hydride. You can also use the hydroxide anion. You can also use carbanium, the negative charge. You can also use cyanide anion. Okay? And then there was some more, I think. There's one, two. Oh, yeah. You can also use the icoxide anion too. Okay? Icoxide anion. And there's some of the neutral nucleophile you can use, which is water. You can have some alcohol too. You can also use ammonia. You can also use amine. So as you know, they all have pair of electrons and can be easily donated to the electrophile. So those are the ones that some neutral nucleophile, but or negative nucleophile that can donate to the electron, pair of electron to the your aldehyde or ketone, where you have very electron density poor carbon there. Okay. So one of the example obviously is the water. Okay. So we try to do the hydration here. So if that is the case, I'm gonna do in a two different way. So what I'm gonna do is you have either ketone here. Okay, I'll show you the reaction first. I'm sorry, and then I'll do the basic and exit conditions later. So what happened to the ketone? When you do the hydration here, which is you have water here. Okay. So when you do the hydration over here, this ketone also can be hydrated like this. Okay, so it can be hydrated, but the problem is this will be also in equilibrium. For ketone, the reverse reaction is actually stronger. So even though you are successfully hydrate your ketone, they go back to the original shape again because their highest stability of the carbonyl groups over here, because the two reasons I just told you like 5 minutes ago. But the aldehyde, or you can actually make it even more dramatic example, which is formaldehyde. So it's actually two hydrogen here, which will be even more unstable, right? So then this will become easily hydrated. So this will become an hydrogen over there, okay? The hydrogen group here. So this will become easily hydrated here, and it makes, because of your now have water coming in to make another the hydrogen group and the water there. So there'll be here, okay, like there. So this is H2O. So anyway, so if that happens, we actually have a special name for this one. Is what we call geminal diol. So as you know, diol simply means there are two hydroxy group. But in case you have two hydroxy group on the same carbon, so you have these two hydroxy group on the same carbon here, right? And then we call that geminal. Means there are two hydroxy group on the same carbon there. Okay, so then we call this a geminal diol because it has two hydroxy group on the same carbon right here. And in this case, when you successfully hydrate this compound, formaldehyde, the reverse reaction is not so strong. So you can actually keep that final product as it is, most of them. Okay? So equilibrium is kind of different. It actually kind of explains how does the nucleophilic addition depending on the structure, like ketone or aldehyde, which compound will be more shifted in the what state, either forward or the reverse, so you can have some products there. Okay? Makes sense, right? Okay. All right, so let's talk about the hydration here. So whenever you have carbonyl groups, okay? So either aldehyde or ketone, either they're going to be shifted in one direction, but we do have hydration at a certain point. So we can discuss with the basic conditions, and we can also discuss in the acidic condition. Okay. So obviously the basic conditions, you have a lot of the hydroxide anion for sure. Okay. So whenever you have a hydroxide anion, there's the 3 lone pair there, and that goes to attack this one, which is what? Electron density 4 carbon, and this one actually goes to this one. Okay. So it's make a push and push. So we'll be single bond now, and there will be so this now has no more negative charge because it donated the electron there, right? And then this could have been here, but actually pushed to now up to here, which is more natural because as you know, the oxygen is the one that takes the extra negative charge because it's highly electronegative. And then once you have this one, they also try to grab one of the proton, I guess, but you can say hydrogen in water. Okay, so this goes to over there because it only takes the proton. Then you have carbons that has 2 hydroxy group on the same carbon, so it becomes a diamino-diol here in basic conditions, and this will become what? OH minus. So this is indeed maintained at the very low, very high pH level with a lot of OH minus that's still available there. So this is what you can do in hydration in basic conditions. Okay. The acidic condition here is actually the same thing, but in a kind of a different way. So in here, acidic condition, you have a lot of hydrogen cation for sure. You can say it's almost same as what? You can say the proton plus H2O. So in this case, you're actually going to, this one will pick up the proton over there, okay? So this will become positively charged because now it lost the electron lone pair to be one single bond over there, and then later the water comes in, okay, and then they actually gonna put the attack over here. So then this will become hydroxy group, and you have water bound to there, which is also positively charged that once they donate the proton, and another water will actually grab that one. So they can be what? Neutral, but this one hydrogen will be leaving, and this will become, water will become hydrogen cation. So indeed, this will be happening at the acidic condition, making the other members of the hydrogen cation, or you can say hydrogen cation and water. So this is what you can do with acidic condition here. So here, you're asking why is it happening in 2 different conditions work out the same way? This is some trick I can tell you. So in the basic conditions, obviously you're going to have a lot of hydroxide anion, which is very strong what? Base. Okay. So strong base simply means what? Strong base simply means where did chalk go? Strong base simply means it's very strong nucleophile. It's the same meaning. So in the basic conditions, because of you having lots of very strong nucleophile, they can easily attack the carbon that is electron density poor. So this is how you can do the hydration here. In acidic condition is quite the other way. In this case, you're going to have this one, right? And then this, once you have this form, before you get to the water, this will become very electron poor. Even oxygen and carbon, they have electron density to the hydrogen here. So this region right now is very electron poor, even further from the carbonyl group. So that makes what? Very electron poor electrophile. So even though you don't have a very strong nucleophile, it can be easily attacked the very, very electron poor carbonyl groups. So it's working and actually the other way. So this one is working because it has very strong nucleophile to attack. This one they don't have a strong nucleophile, but they just have very weak, very electron dispersing nuclear electrophile. And looking for some nucleophile, the water should be just good enough, even though it's not so strong as base over there. Okay? Does it make sense? Okay, so I'll move on. So you can try actually one problem here. So do not worry about the equilibrium status. Maybe you can try this one. Either acidic or basic condition doesn't matter. Maybe you can try this one. Okay. And then we'll move on to the next one. Okay, it doesn't matter the base works here. Can you show me the hydration? That would be just good. Okay, but 30 seconds we just. So it takes some time because there's a mechanism. But if you know the tricks, it should be quite straightforward. Okay, so let's try this one. So what I'm going to do is I'm going to do this. So, okay, so you know the trick now, right? So just try to, maybe you can try to remove this one. Okay. So if this is indeed hydration, you're adding this part right there. Okay, that's it. So remove the double bond between oxygen and carbon. So it will be single bond, but with the hydrogen, so it will be hydroxy group. Another hydroxy group will be from the water, so it makes the diol, but also the same carbon, so it will be our geminal diol. Make sense, right? Okay. Yeah. So we didn't. All right. So So the next nucleophile formation you can try is we call cyanohydrin formation. So we actually gonna do the same thing over and over, but what we're gonna do is just switching the nucleophile. So I just did, okay. So hydration is what? H2O, right? So it's H2O here. And remember, this is our nucleophile, and this is the hydrogen here. Cyanohydrin, we're gonna do HCN. Okay? So this is where you can have a one. Cyanide, anion there, right? Like this one. So it is going to be always paired with the hydrogen and your potential nucleophile. What you can do is, if you have this one either ketone or, well, you can try the aldehyde because it's more active. If you do the HY form, what happens to this one is the RCOHY. Oh, let's do R because it will be easier to look at. R prime. So you see the parent, the hydrogen goes to the oxygen, Y attached there. Okay. So this is if that is water, will become right. You adding hydroxide here, and you just adding hydrogen here. That's what happened. What we just did. So I'm gonna do the same thing over here. Oh, yeah, eraser, yeah. So I'm gonna do the same thing over here with the different nuclear gun. That's it. So we're gonna do this a lot. But if you know this trick, it's actually become very simple. You just have a hydrogen with the nucleophile. Hydrogen goes to the oxygen. The Y part, whatever that is alcohol. Alkoxide or any other goes to the additional groups on there. So if you have this one, okay? You know what this is, right? This is a benzaldehyde we learned before, and you can treat it with the this one, okay? It's cyanide anion. Okay? So what you can do is they actually gonna add it to there, and this will become negative. Okay, so once you have this group added to your carbon, the double bond will move to the oxygen, right? So it'll be negative. Okay, and then you can treat it with HCl again, and this hydrogen cation will be taken by this negative charged oxygen here. So it will become like here. Okay, so you saw the same thing, right? If you treat this benzaldehyde with the HCN, okay, you're just going to have what? This group added to here, and this oxygen in the carbonyl group will have hydrogen with the single bond. So this is the trick. This is what we're gonna do even on next Monday. Okay, so we'll do this a lot on Monday, and then hopefully I can finish the lecture by Wednesday, and then we can have 2 review sessions, either this coming Friday or the Monday, because we have exam on April 7th and 9th. Are you guys in the Friday section, right? Yeah, that would be 9th of April. So we still have quite a time, but this will tell you a lot anyway already in these chapters. And the last chapter is very short, so we're in a good pace. Okay, so let me stop here. I don't want to